In section 8.1, we are going to talk about sequences and series. And our objectives here are to be able to use sequence notation to write the terms of sequences, use factorial notation, use summation notation, find sums of infinite series, and use sequences and series to model and solve real-life problems. So with sequences, instead of using function notation, they're usually written using subscript. So when we're writing an infinite sequence, we would number them in terms of the actual term number. So you would have your a sub 1, your a sub 2, your a sub 3, your a sub n, and then you have the dots, which tells you that it's an infinite sequence. If it was a finite sequence, then it would end at a particular value. So if it was you had 7 terms, then it would end at a sub 7. Every once in a while, especially if we're starting with an initial amount and we're looking at time and years or something, we'll use a sub 0 as our starting amount. And then that way, like your a sub 1 would be your amount after 1 year, and your a sub 2 would be your amount after 2 years. So every once in a while, you will see that a sub 0 notation as your first term, but it still works the same way that if you have a sub 1. So for this first example, we're just going to work on writing the terms of a sequence given these equations. So our first 4 terms, that means our first term, so a sub 1 would be when n is 1. So we'll plug a 1 in for n. So you would say 3 times 1 minus 2 would give you 1. So a sub 2 would be plugging in a 2 for n. So 3 times 2 minus 2 would be 4. A sub 3 would be plugging a 3 in for n. And we'd get 7. And then a sub 4 would mean you plug a 4 in for n. And you get 10. So those would be your first 4 terms, 1, 4, 7, and 10. For part B, if we do the same thing, we have 3 plus negative 1 to the 1. So you get 3 minus 1, so you would have 2. Your a sub 2, you would have 3 plus negative 1 squared, which would be 3 plus 1, so 4. Your a sub 3 would be 3 plus negative 1 to the third, so you do back to 2, and so you kind of see what that pattern here would look like. When you're raising it to that even power, you would have the positive 1, and the odd power, you would have the negative 1. So a recursive sequence is when you need the previous term. Remember, we talked about that in kind of the last section. So this a sub k minus 1 right here, this means that we're going to substitute in the previous term, or the value of the previous term. So if we know our first term is 3, then to find our second term, we're going to do 2, because there's a 2, times, and this means the value of the term before the one we want to find. So if we want to find the second term, we're going to plug in the value of the first term, which was 3. So 2 times 3, and we get 6. So the third term, we keep the 2, but now we have to plug in the value of the second term, the previous term. So 2 times 6, and we get 12. So fourth term would be 2 times the previous term, which is 12. You get 24. And then the fifth term, we have 2 times 24, which gives you 48. The next thing we're looking at is your factorial notation. So just that reminder that if you see a number with that exclamation mark after it, you're just multiplying 1 times 2 times 3 all the way up to whatever that number is. And 0 factorial equals 1. So for this example, we're going to write the first 5 terms of the sequence given by 2 to the n over n factorial, and we're going to begin with n equals 0 as our first term. So a sub 0 is our first term, which means we would have 2 to the 0 over 0 factorial. 2 to the 0 is 1, 0 factorial is 1, and we get 1. So a to the 1 would be 2 to the 1 over 1 factorial. So that would just be 2. 1 factorial is just 1 times 1. So we get 2 times over 1, which gives us 2. A to the sub 2 would be 2 to the 2 over 2 factorial. So we would get 4 over, and I usually start with that number, so I would say 2 times 1, which gives us 2. A sub 3 would be 2 to the 3rd over 3 factorial, which would be 8 over 3 times 2 times 1. So 8/6 would be 4/3. And then a to the 4th, right, it's really our 5th term since we started at 0. So we get 2 to the 4th over 4 factorial. So 16 over 4 times 3 times 2 times 1. So we get 16 over 4 times 3 is 12, times 2 is 24. So we get 16 24ths, which is 2/3. So another notation we need to talk about is your summation notation. And that's that kind of that big E value right there. And so what this means is that we're adding up all of the terms. So this a sub I, where I, in this case, it tells you I starts with the first term, and the number on the top tells you where you're ending. So you're going through the nth term. I is called the index of summation, and n is the upper limit. So in this case, it tells you you're adding the first term through the nth term. And so you would just have to add those up based on what your A values are. So this was kind of already written out for you as what it looks like, and we can just simplify these. So in this first one right here, we're going to add the first through the 5th term of 3 times I. So what we do is we actually plug in those terms for I. So we have 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4, and we end at 3 times 5 since we were going up to our 5th term. So you would have 3 plus 6 plus 9 plus 12 plus 15, which gives you 45. If we look at B, this time they didn't use an I, they used a K, and it's okay, it's just a letter. So this says we're adding the 3rd through the 6th term, and we're plugging those in for K. So we'll start by plugging in the 3. So you have your 1 plus 3 squared, 1 plus 4 squared, 1 plus 5 squared, and we go up to the 1 plus 6 squared. So you get 10 plus 17 plus 26 plus 37, which gives you 90. And then part C, we've already worked out for the most part here. But again, you're starting when n is 0, and you're going up to where n is 8 of 1 over n factorial. So you have 1 over 0 factorial, plus 1 over 1 factorial, plus 1 over 2 factorial, all the way up to 1 over 8 factorial, which simplifies into all of these fractions right here. And if you end up putting all of those into your calculator to get a decimal, you get about 2.71828. So some properties of your sums is that if you have a constant, like a constant's just a number. So if you were adding the sum as I goes from 1 to 4 of 2, your sum is just going to be the constant times your n value. Something else with it is that if you have a constant here, you can actually put it out to the front. So sometimes that will make your values easier. If you're adding two different things, you can actually kind of distribute those summations. Same thing with if you're subtracting those, you can distribute those summations. So now going into series, many applications involve the sum of the terms of a finite or infinite sequence, and the sum is called a series. So the difference is the sequence is just a set of numbers. A series is the sum of all of those numbers. So that formal definition says, consider your sequence the sum of the first n terms. So if we add a finite number of terms, it's a finite sum. And if we add an infinite number of terms, we can actually find an infinite sum. So if we want to find the sum of a series, this is when you're going to look at your formula sheet. And we're going to use our formula sheet to help us out here if we're finding sums of finite or infinite series. Now on our formula sheet, we have the sum of an infinite geometric series. So if we can determine that our series is geometric, and we really haven't gotten into that so much yet here, but the geometric part is you're just multiplying to get the next term. So if we're multiplying to get our next term, we can use our formula for it. If we're not, then we just have to look at patterns. So for this first one, for the third partial sum, for part A, that really means though for part A, we're adding as I goes from 1 to 3 of 3 over 10 to the I. So on that one, we're adding 3 over 10 to the 1 plus 3 over 10 to the 2 plus 3 over 10 to the 3. And so if we think about these as decimals, 3/10 is just 0.3. 3/100 is 0.03. 3/1000 is 0.003. So if we add those together, we get 0.333. And so if we go to part B, if we were adding the sum as I goes from 1 to infinity of 3 over 10 to the I, if you look at the pattern of what we had, when you have your 3 over 10 to the 1 and 3 over 10 to the 2 and 3 over 10 to the 3, which was from before, if we kept going, right, we'd follow that same pattern that we had up above, where you have your 0.3 plus 0.03 plus 0.003. So we keep throwing another 0 in front of the 3, right? And we keep going. So eventually what happens is we get 0.3 repeating because we can continue that pattern forever. And so you end up with 1/3 for that. In example 10, we have compound interest. So we have an investor deposits $5,000 in an account that earns 5% interest compounded quarterly. The balance in the account after n quarters is given by this equation. So we're going to use the information to write the first 3 terms of the sequence, and then we're going to find the balance after 10 years by computing the 40th term, since this is all broken up into quarters. So our initial, our A sub 0, right, because they tell us that n is starting at 0, would be 5,000 times 1 plus 0.03 over 4 to the 0, which we know that that quantity is 1. So A sub 0 is 5,000, which makes sense because that's what the investor initially deposited. So A sub 1 would be 5,000 times 1 plus 0.03 over, get rid of that decimal there, over 4 to the 1. And if you calculate that, you type that in, you get 5,037.50. And I would put the 0 there because we're talking money, so that's 50 cents. And we want the first, what did it say? First 3 terms. So our a sub 2 would be our third term, which we would get by doing 5,000 times 1 plus 0.03 over 4 to the 2, which would give you 5,075.28. So then for part B, find the after 10 years. So 10 years will have 4 quarters, which is why we have to plug in a 40 for our n. Right? So a sub 40 would be 5,000 times 1 plus 0.03 over 4 to the 40th, which gives you $6,741.74. And then our last example is writing an explicit formula or recursive formula for a sequence. And so remember, we have our explicit formula and we have our recursive formula. And recursive, we sometimes go like that. And so if we want to write a formula for a sequence, we usually have to identify what that first term is and what the difference is for the sequence. So to write our explicit formula, which is this first one here, this should be, instead of saying a sub 1, this should say a sub n, because it's just an n. So our explicit formula, we would say, is a sub n equals the first term, which is 1, plus the difference in your terms. So when you look to go from 1 to 4 and 4 to 7 and 7 to 10, our difference is going to be 3. So 1 plus 3 times n minus 1. We could distribute the 3 to simplify it. So a sub n would equal 1 plus 3n minus 3. Or a sub n would equal negative 2 plus 3n. So that would be one way to write. That would be your explicit formula. If we needed to write our recursive formula, so maybe we'll make a note here that this is our explicit. Our recursive, we always need to start with the first term, which is 1. And then we say to get the next term, we're going to take the previous term plus the difference, which was 3, for n, and you could say is greater than 1 or greater than or equal to 2. They mean the same thing because greater than 1 would mean it has to be 2.